Hello, my name is Andrej, and today I'll be presenting a paper called Learning Gradient Fields for Shape Generation. I'd first like to start with trying to cover what this paper is trying to achieve. So, given a data set full of points, either 2D or 3D, in this case we'll be using ShapeNet, we want to create a generative model that will represent these point clouds. And ideally, we want to be able to sample an arbitrary number of points from these points. Going on to why we want to do this in the first place. Well, the thing is, point clouds are really only samples of the underlying object behind it. So we would like to actually sample that object and have a model for that object rather than the points themselves. Why is that useful? Well, in the cases where points are sparse, we can actually try to figure out what the underlying structure is. We can complete the structure in cases where we don't have full information. And we can also determine other properties such as mass, volume, inertia, anything that we deem useful. In terms of prior works, there are three main camps. The first camp focuses entirely on using point clouds directly. So why is this useful? Well, the data is already in point cloud format, so there's no extra information or extra processing that we need to do, and that makes it very efficient. However, it does have its drawbacks. Some of these methods assume a fixed number of points. Others use some heuristic functions that they determine to work well. And others actually assume an ordering to the number of points, which, if the ordering was not exactly the same, they would fail. And in the case of point cloud GAN, it has unstable training. So that moves us into the second camp, which is 3D representations. There are three main ways to represent the objects in 3D. We can use voxel grid, which is a regularized grid of 3D space. We can use meshes, or we can use, more recently, implicit representations. So these are fantastic because they actually try to model the 3D object directly. However, in the case of implicit representations, it requires us to compute a science distance function, which is computationally expensive. And same with the other ones as well, especially meshes. Trying to produce a watertight mesh is quite expensive to compute. So that brings us to our third camp, which is energy-based modeling. And this is actually what this paper is going to try to build off of. Specifically, we'll try to build off of the work done by Song, which was done in a 2D case, and we'll try to extend it to a 3D case. And the nice thing about this is that even though it's a statistical method, they're able to use these probability distribution functions without having to normalize, which is usually extremely computationally expensive. And that's what makes it efficient. And this is what we're going to be building off of. So what are the main contributions? Well, like I said before, we're taking a whole new approach to modeling 3D distributions, which previously was done on 2D, but we're going to take it to the 3D case. This method is extremely robust to sparsity, and it's quite computationally efficient, or so it's claimed to be. Some key insights are that we are actually able to create implicit surfaces without having to worry about generating a mesh and computing a watertight mesh around objects. And we're actually able to also generate new objects by interpolating the latent space representation. And lastly, this paper achieves state-of-the-art performance on autoencoding and the generation of point clouds. So just a quick overview of what our problem setting looks like. We're going to start off with a set of shapes. And each shape is going to be defined by a set of points sampled from their surface. And we can model the surface in two ways. The first is to have a uniform distribution along the surface. However, it is discontinuous because any point which is not on the surface has a probability density of 0, whereas anything on the surface jumps to a finite probability. And so in order to learn the surface, we're going to apply a Gaussian kernel approximation, basically add Gaussian noise, in order to make that, gradient more smooth. So kind of the first idea that comes to mind is, why don't we model the distribution directly? And this is what's done in prior works. However, it's quite computationally expensive to compute that. And so an alternative idea is actually just to model the gradient of the log probability of that distribution, and iteratively sample points from a prior distribution and try to get closer and closer to the actual shape. And this will allow us to sample an arbitrary number of points very efficiently. So our end goal is to have a neural network that approximates this distribution. Moving on to the method, how do we actually sample these point clouds? Well, what we'll do is we'll start off with a random distribution, and we'll iteratively take these points, move them in the direction of the gradient, and update their position until we get to a steady state where it's along that surface. And in this case, that involves 10 different iterations going from a large Gaussian noise to a small Gaussian noise. To generate multiple shapes, we're going to use a GAN autoencoder, where we're going to encode into a latent variable z, and at runtime we can flip a switch and take the latent variable generated by the GAN and use that to decode the actual shape and sample points from that and see what shapes we get from that. And the last thing that we're going to try to do is we're going to try to generate an implicit surface. So the key insight here is that the surface is defined by the area of the maximum probability. And so what we can do is we can raycast a ray, keep going in the direction, and if we hit a point where we have a gradient of 0, we know that we're along the surface and we can stop. Otherwise, we can continue going, and if there's no 0 gradient, then we consider that as background. And for small variances, this works because the zero probability, the 0 gradient, relates to the surface itself. Moving on to results. Here you can see some upscaling and some implicit representation results for 3 different categories. The columns on the left represent 248 points, whereas the columns on the right are sparse points, 256. And you can see in both cases the upscaling and the implicit representations are very close and true to the actual shape. Moving on to some quantitative results, we can see here that it actually performs quite well. There's two performance metrics that we're using. One is chamfer distance, and the other one is Earth's mover's distance. And the main idea here is that they're point-to-point distances where we sample points along the surface, and then we see how close the output points are to those points along the surface. Now, because these metrics are point-to-point and not point-to-surface, there is a chance that the generated point and the sample point, the ones that are the closest to each other, are not, even though it's along the surface, will have some error associated with it. And that's what this column on the right is trying to tell us. This is the oracle column, which is if we were to sample random points along that surface, what would the optimal error be? So it's our optimal lower bound. And you can see in most cases we get very, very close to the optimal lower bound. Moving on to upscaling. So in this case, what they're doing is they're training and sampling, both at training and runtime, with varying amounts of sparsity. And you can see that the performance doesn't actually change all that much, indicating that we're able to deal with sparsity quite well. And again, this is some of our generation results. You can see we're also performing quite well, similarly to previous methods. So as a key takeaway, it seems that we're able to accurately and uniformly model distribution. We're quite robust to sparsity, and we're able to achieve state-of-the-art results. That's not to say that it doesn't have its own limitations. The key criticism that I have for this paper is that for all the talk of runtime complexity in prior works, there's actually no runtime analysis, so we actually don't know how well it works. Then another criticism would be that, sure, this works in a simulated world where we sample points. However, there's nothing to say how it would work in a real scene with noise or points sampled from other objects that are missegmented, for example. There's also some other criticisms, even though it's a fairly recent paper. There are some criticisms where they say that it's limited to reconstruction of single objects, and it also doesn't necessarily work in scenes that were not seen during training time. Just to give a quick recap, again, this is a novel way of trying to represent 3D objects using their point clouds. It's able to deal with sparsity very well, and it's also, in theory, very computationally efficient. Some things to take away: we're able to generate implicit surfaces without the need to generate meshes, and we're able to generate new objects fairly well by interpolating the latent space. And of course, we've achieved state-of-the-art results on auto-encoding and generation of point clouds. Thank you for your time.